All right, welcome to the third version of the AP Environmental Science Lectures. My name is Mr. Wando. And this one is going to kind of be a little chemistry review. It's about science, matter, energy, and systems. Part of it is kind of what scientists actually do. And this picture is taken of a field experiment, a pretty well-known field experiment known as the Hubbard-Brook deforestation experiment. And what you have here is a couple different plots of land. We've got our completely deforested region on the left here, and then over here we have the untouched version where they did not remove any plants or anything. So on this side we took out all the trees and shrubs, and there's a stream that runs through each of these portions, and they measured the amount of water that left the stream, the runoff, and the amount of nutrients in soil that was eroded. So our control would be this untouched forest on the right. This is our control variable, and they use that to see how much water would normally run out of the stream. The deforest one, that's our experimental group, and what they found, the results of this controlled experiment, were that there was 30 to 40% more water leaving the deforested side and about 8 times more nutrients lost from the soil. There weren't roots or plants to help hold the soil in place, and so when it rained, a really large amount of dirt was taken into that stream along with a lot of water that was not retained and just kind of ran out of that ecosystem and down into the stream and so on and so forth. So that's kind of what scientists do, and there's two big parts here. There's theories and laws, and they're pretty easy to get confused with one another. A theory is something that's supported by overwhelming scientific evidence. It's going to explain why something happens. This is like the theory of plate tectonics. We don't have physical proof, we can't see it in action, but there is a lot of science that shows that it exists. In plate tectonics, you've got the fact that the continents kind of match up. If you stuck South America and Africa together, they fit together like puzzle pieces. And then if you look at the rocks on either side, you got similar rocks and similar types of fossils. And so we can say that at some point in time, these land masses were probably stuck together. You have a lot of people that don't fully understand what a theory is, and the fact that theories can kind of change over time as we get more evidence. Some people don't take them as seriously as they really need to. A theory is a very heavily researched proposal, and it's something that we have seen supported time and time again. So a lot of science goes into supporting theories, and they're not to be taken lightly. A law is much shorter and much more specific. So this is a description of what we find. And an example of law would be like the law of gravity, which simply says all things with mass exert a force of attraction. That force of attraction is related to how much mass they have. So essentially, if I hold a book and I release the book is going to fall towards the center of the earth every time. And it's just describing that it falls every single time. We can do a couple different laws in this portion of the unit, and they're really important for the rest of the unit. They kind of set the ground tables for us to work from. All right, up on the top right corner, here's our scientific method. That's kind of how the Hubbard-Brook experiment went along. We had a question: how does deforestation affect the forest? And so they did some research, and they found that they didn't have any exact sources or studies run on this problem they had. So they came up with a hypothesis. Maybe if we deforest, we are risking losing water from that ecosystem, or quickly letting it run across the soil and out down the stream. So they designed and conducted it. They deforested one side. They set up the dams on each of the streams to measure how much water and how much sediment gets lost. And then they drew the conclusions and reported the results. And it's a pretty well-known study. One of the big principles of chemistry you need to understand for this is matter, and part of that is the difference between elements and compounds. Elements are kind of the building blocks. It's as simple as it gets. A single element, it's just one type of substance. We can't get any other substances out of it. Compound is two or more elements that are held together by chemical bonds. We can break bonds and make bonds. Breaking bonds is typically going to release some energy, while making bonds is typically going to cost some energy. I picked out oxygen, and we've got a diagram of an oxygen atom in the top right corner here. So in the nucleus, remember we've got protons, neutrons, the protons having a +1 charge, and the electrons would have a -1 charge. The electrons are found orbiting the nucleus. On the periodic table, you've got a couple important things. At the top is the atomic number. That is the number of protons in that element, and you will never find an oxygen atom that has a different number of protons than 8. The O would be the symbol, that stands for oxygen, and then on the bottom is our atomic mass. The atomic mass of oxygen is close to 16, and the reason being it has 8 protons and 8 neutrons, that each of them have a mass of 1. The mass of an electron is negligible, so we just assume that it is 0. I said that every oxygen atom has 8 protons. Not every oxygen atom needs to have 8 neutrons. If you have a different number of neutrons, that is known as an isotope. All right, the properties of it aren't significantly different. Some isotopes are more rare than others. Some of them are radioactive, while others are perfectly harmless. But it's still an oxygen atom. Oxygen can also have a different number of electrons, so they can be gained or lost through bonding. And when they are gained or lost, we pick up a charge, right? If you lose some of that negative charge by giving away electrons, you become more positive, and you end up with a positive charge. We can do the opposite. We can gain extra electrons and become more negative, and that is matter. All right, we can break apart matter into high quality and low quality matter. And the quality is based on two different things. It's based on how available it is and how concentrated it is. The more easily available matter would be known as high quality matter, while the more concentrated matter is also going to be higher in quality. And so it's kind of a range of things. We don't just have this is high quality, this is low quality always. It's kind of a range of things. And something that's highly concentrated and easily accessible would be things like the turkeys in this turkey farm, right? You can see just how many turkeys there are in a small amount of area. It's very high quality matter, and we're talking about turkey meat in this case. You could have a oil deposit, which would be high quality. If it's a large oil deposit that's close to the surface, you can get to it very easily, and it's got pretty good concentration. On the lower quality end of the spectrum, that might be something like our shale gas that we frack for throughout the whole world. That shale gas is it's easily available, but it's not really that concentrated, and it's not as easily available as an oil well might be. An oil well where you kind of have an underground pocket full of oil, while shale gas is natural gas, which is in the gas phase, and it's spread out through porous rocks, and so they actually have to break apart the rocks and then put a pipe down there and let that pipe pull up that trapped gas. So it's a lot lower quality than our petroleum deposits that we have throughout the Middle East or in the Gulf of Mexico, for example. And this herd of wild turkeys out here, this would be an example of low quality matter. So we have a much larger scope in this picture. The landscape shot's a lot bigger, but we have much fewer turkeys. They are less available and less concentrated, so they'd be lower quality turkeys than what you see over here. Doesn't necessarily mean that their meat does not taste as good or is not as good of a replacement as our farm turkeys. In fact, you'd probably have a lot of people argue the opposite, that these wild turkeys taste better, but matter quality is based on availability and concentration. Some really low quality matter examples in the real world would be things like a deep underground aquifer. So an aquifer that's more than 400 feet below the ground is going to be a lot lower quality than something that is higher up. All right, we've got matter, now we've got energy. Energy is the capacity to do work. Anytime you are moving a force over a distance, you are doing work. And we have the potential to do work. That is stored energy. It's usually stored by position if we're talking about gravity, or it can be stored in chemical bonds if we're talking about chemical potential energy. And I picked out this dam here. This is actually Rodman Dam, which is just northwest of Jacksonville. But we've got water stored above that dam, and gravity's got the potential to pull it down. The water gets deposited up there through rainwater that falls above the dam, the natural spring, the artesian aquifers that feed the dam, and then it runs down through. And we could put a turbine on here and collect that energy that is being released as it comes through the dam, and that would be hydropower. We also have these wind turbines down here. These would be an example of kinetic energy. So as the wind blows, it spins the turbine, and that kinetic energy is converted into electrical. And just like with matter, we've got high and low quality energy. So high quality energy is something that's got a great capacity and it's got a high concentration. So something like oil is extremely high quality energy. It has a lot of potential. Think about your car, how heavy it is, how tough it would be to move it by hand without a internal combustion engine. And then think about how much gas you burn on a trip just from home to school. It's probably less than a few gallons of gas, which is a tremendous amount of energy to move that weight that distance. So something like oil is extremely high quality energy. Things that are low quality energy are like the latent heat in the atmosphere. That heat in the atmosphere that is just kind of out there is not really that useful. It's not very hot heat, and it's not very concentrated. So we can't really use it for much except keeping our bodies warm enough that we don't freeze. Energy conversions. These two laws are really important for energy conversions. The first one is simply the law of conservation of energy, which means the amount of energy can never change. We always have the same amount of energy. We can't create it. We cannot destroy it. Our energy, of course, comes from the sun. The sun goes through a process called nuclear fusion, in which case it is combining atoms together. And when it does that, it releases some of that mass and converts it into energy. That energy travels across space and radiates down through our planet, and then we can use it for whatever we want to use it for. The second law is a little bit different. What it says is that energy is lost to less useful forms at each energy conversion, which means every time we convert that energy to a new type, we're losing some of that energy to less useful forms. And in most cases, that less useful form is that latent heat I was telling you about on the previous slide. And so I put a picture of my truck, right? This is the truck that I drive. It's 2003 Chevy S10, nice brown color to it. I think the dealer called it sandalwood to make it sound a little fancy, but it's brown and it's kind of ugly. But it gets me from point A to point B. The useful form of energy that I'm putting into this truck is gasoline. It stores chemical energy in the bonds, and when I push my foot on the accelerator, I am injecting gasoline into my pistons, and they are igniting the gasoline, and it is driving the pistons up, which spins my axles and propels me forward. So my overall goal here is to move my car from point A to point B, and I put in a lot of energy in the form of gasoline to do it. The internal combustion engine in my car is not really that efficient. A lot of the energy stored in that gasoline goes to things that aren't getting me from point A to point B, like heat. Right after you drive your car for a certain amount of time, that engine will get extremely hot, and you can even feel it by putting your hand on the hood of the car. That heat did not assist you in getting from point A to point B, so we would call that a useless form of energy. It also makes a sound, right? My truck, you can hear when it's on, and that sound is not helping me get from point A to point B. So that would be another useful or useless form of energy. It's not helping me accomplish my goal. Systems. A system is kind of a set of components that interact and function in a regular way. Some examples of systems would be like a human body, right? There are a lot of different things in your body, the organs that work together, and they work together in a regular way. And there's some inputs, there's some outputs, and if you keep everything in the middle, you end up all right. There's also a rivers as a system, and you can have the economy as a system. So anything that's got a set of components that functions in a regular way. These systems all have inputs and outputs. The inputs are things that go in. Outputs would be things that go out. So if you think about a river, things that go in the river. You've got rainwater that enters the river. Soil that erodes enters the river. Things that come out of the river. The water might evaporate further down the river. It might deposit rocks. When it floods, it may take out trees and stuff. So there's a lot of different inputs and outputs. One of the things that we're going to spend a lot of time focusing on throughout the year are feedback loops. And feedback loops are things that can happen when a system undergoes a change. The first one I want to talk about is the positive feedback loop in the top right corner. Positive feedback loops are very bad. A positive feedback loop is a really bad thing, and the reason why is it keeps getting worse and worse and worse as it goes. One example of a positive feedback loop is the never-ending cycle of population growth, right? So you have more people being born every day. Those new, larger amount of kids, once they grow up to adults, they're going to have even more kids because there's more parents to start with. And so it keeps on growing and growing and growing. This is another example of positive feedback loop, one of them that's blamed pretty heavily on global warming. So as the temperature rises up, what does that do? Well, it starts to melt some of that Arctic ice on the North and South Pole. That ice is very white in color, and it's got a very high albedo, which is its ability to reflect heat. And so as it melts, we're replacing white reflective ice with dark colored, dark blue, dark green colored ocean water, which absorbs heat very well. And so it absorbs even more heat, which warms up the local environment. In turn, that melts more ice, which lowers the amount of sunlight we're reflecting, and so on and so forth. And you end up with a never-ending cycle. So a positive feedback loop is one where a change creates more changes in the same direction. So by getting warmer here, we continue to get warmer and warmer and warmer and warmer, and it's just going to spiral out of control, right? Nowhere on this loop does more ice get created. We don't have any kind of balancing effect. A negative feedback loop is a balancing effect, and a really good example of a negative feedback loop is the thermostat in your house, right? You can set the temperature to that thermostat, and if it gets too cold, right, room temperature drops, that tells the thermostat, oh boy, time to work, and so it turns on the furnace. Furnace heats the home, temperature rises up, that gets relayed back to the thermostat. The thermostat says, okay, well, we're good now. We don't need to run the furnace anymore, and it turns the furnace back off. And then it waits for that signal again to tell it to go and turn itself back on. So these negative feedback loops are a really good thing for the environment, right? This is kind of nature's way to regulate itself. Our bodies do the same thing with temperature, right? When you get really hot, you start to sweat. Once you cool back down, that sweating cuts back off because it's a negative feedback loop. It was told to stop. A really good example of a negative feedback loop that we all can have a part in is recycling, right? So picture your aluminum soda can. Initially, that aluminum had to be mined out of the ground and processed into usable aluminum. Once you use it, you have the option of recycling it. And so you would put that aluminum back in the beginning of the process. By restoring that fresh aluminum, we don't need to mine as much virgin aluminum back out of the soil. So we can reduce our mining, which in turn kind of slows it down. So it's a self-regulating system by recycling. Kind of the big three takeaways here. There is no way, meaning that the law of conservation of matter says we can't create or destroy matter. So the stuff that we try to get rid of, throw away trash, we try to hide the oil that BP spilled in the Gulf of Mexico, we can't really get it anywhere. There is no way. We can't take it out of the environment. It's got to go somewhere, in most cases for trash that's buried deep underground and then sealed and forgotten about. The second big takeaway is you can't get something for nothing, meaning that energy has to come from somewhere. We cannot create or destroy energy. No matter how smart or technologically advanced we get, this is a fundamental law of physics, the first law of thermodynamics. We can never create energy for free. It always has to be converted. And because of the second law, you cannot break even. We can never end up with as much energy as we started with. Every conversion loses some. No matter what type of technological advances we have, how efficient our vehicles get, we will never break even. We always are going to lose some energy to heat or to sound or to light that is not useful or something we can't take with us or put to our purpose. That's all I've got for the third lecture here, so I hope you enjoyed it. Please bring your notes to class tomorrow and any questions you may have about this quick little chemistry review. Thank you.